In this particular this module or this interactive session, I'll try to discuss very selective topics because I have not seen any query from your side in the Google set, as well as that I didn't find any queries related to any other forum. So that's why before that, I'm just presenting which is more important, or maybe which is maybe try to give some overall view of this particular course. So that selective parts I'm trying to present in this interactive session. So I think we have already covered the week. I think already. I think this is the week 11 is going on, and maybe next week is a week 2. That will be the final week. Will be there. But I'll try to focus on the content related to the week 10 and 11, and because 12 is not done till yet. So here, few selective topics. You see that 11 week 10 and 11, it contains usually that non-conventional processing and steel processing. So here you can see that the content of this non-conventional processing is basically ceramic and polymer and ceramic coating, different tape casting process, and colloidal processing and casting process, and of course injection molding and extrusion process based on the dispersions and additive processes. So these are the basic, these are the contents, or maybe you can say that subtopics related to the non-conventional processing of materials. Apart from that, there is steel processing, because this steel industry is very important in this particular course. Therefore, we more focus on the one particular module that is related to the steel processing. So in steel processing, we'll try to describe the introduction to the steel making, then what way the single crystal production is done, how to understand the flow analysis in the steel industry, and of course the solidification behavior, which is more important associated to steel processing. And that we'll try to describe in this particular module. Now, these references already we have already discussed. If you really interested to look into this particular topic, you can find out all the related topics within this references. So very specific. If you're interested to fundamentals of solidification, then you need to go for the reference 7. If you understand the fundamentals of heat transfer, which is maybe utilized in case of the metal casting process, then reference 9 is the best option. And of course, metal forming process, we get some references also. And overall materials processing, maybe good reference is the reference 1. So each and every topic is associated with some kind of the reference book. So in details, you'll get more information about the topic related to the different kind of the references. Now I already mentioned the types of the questions and the different weeks. Maybe the similar, you are already solving the different assignment problems. So you can see observe the pattern of the questions also in the assignment problem. So you can expect the similar kind of the questions will be there in the final exam. But of course it will be based on the small numerical problems, based on the this theory, and based on the some expression formula you have utilized for this in this course. So try to learn all this formula, and so that it will be useful for your final exam. Now I'll come to this topic. One is which is one important, the non-conventional materials processing is the colloidal processing and casting. So in this particular module, the slip casting is one important manufacturing processes for the ceramic components, because ceramic components we cannot directly manufacture like other metallic materials. So in this ceramic materials, with the processing technology is little different. So in this case, this name is known as the slip casting process. Slip casting process is basically mainly defined in case of the ceramic material. So we make a slurry using the ceramic powders, very fine powders, or we can say the very fine clay, which is known as the slip. So taking this clay and make a slurry, and the slurry has to be put in some kind of the porous material. So in this case, when we put it, the ceramic slurry in a porous material, and through this porous material, this water or maybe the solution will try to, or maybe I can say that if the slurry component, main component is the water, so that will passes through this porous media through the capillary action. So then water will be drained out, and then in that case the concentrated fine particles along with the binding in the form of a binding, it will be deposited over the surface. So that from the figure it is very clear that we fill with the complete mold using this ceramic slurry. Then we allow some time. So over this time, the thickness will actually increase. So once it is certain span of time, then we can take the excess slurry out from the mold, and you can observe there is a certain thickness deposited over the mold surface. So this thickness actually depending upon what is the time we are putting this thing and effectiveness of this porous media we are utilizing in this case to make the mold here. So once it is done, we make take it out from the mold. You can dry also, we can do post-processing to get a very smooth finish is possible to produce. So this is the basic philosophy which we follow for the processing of the ceramic material. But of course, in this case, one important point, this process is not fast actually. This process is actually very slow process. So to make it fast, this particular process, we can take different way. We can take different measurement for that. Say one is the pressure casting process. In this cases, we can apply the pressure to the slurry such that the diffusion of the water through this porous meter will be the rate will be much high. So that is one way to increase the casting rate. Second part is the vacuum assisted casting. So instead of pressure, we create the vacuum also. That will also help to make a pressure difference and just increase the rate of the casting process. Apart from this, we can use the centrifugal casting also. We can use the centrifugal force in this case to make it to enhance the casting rate also. So these are the different ways to enhance or make the faster of this casting process and for the ceramic material. So application, of course, there are lots of applications for this particular process, slip casting process. We can use the dense refractories of the very complex shape, very thin wall products. We can create even large structural refractories also can be produced using this slip casting process. Now, another process that is the coating and the tape casting process, which is one of the another non-conventional processes. We use the coating is important, and one of the coating. The typically coating process is known as the tape casting process. So tape casting is basically special type of the coating process. In this case, is basically tape casting is used to produce very thin ceramic sheets, and that is also from the ceramic slurry. So in this case, first dispersion is created, and that is containing the ceramic particles and with some binders. Usually the polymer binders is used, and that is actually coated over a substrate. So in this case, the liquid dispersion is basically deposited and spread over the substrate and allowed to solidify this thing. So in this way, we can create very casted in a very thin layer of the ceramic, and usually the flat surface in the form of flat surface. Of course, the shape of the flat surface thickness can be controlled. And once it is created, using this by controlling the viscosity of this slurry, we can create the flat surface, and after that, with the dry and sinter operation can be performed such that it will becomes more harder, and it can be finally we can use it after sintering or drying process. So in this case, the tape casting is basically very well-known technique that associated with the ceramic membrane production. Similarly, we can use the several ways the ceramic coating also. So ceramic coating is nowadays extensively used, and basically we use the surface modification to achieve certain properties of the surface. And usually, mainly the purpose of the ceramic coating is basically to prevent the corrosion resistance, and of course the resistance from the oxidation for the alloy. And as well as that, even if you put the very hard ceramic coating over the surface, it is possible to avoid the wear damage of the surface. So that's why we use the over the surface very thin layer of the ceramic coating is basically nowadays it is very useful, and you can find out lots of application, practical application. You can see the ceramic coating over the alloy system. Now, ceramic coating is actually try to create some kind of the hydrophobic surface. Hydrophobic surface means basically keeps off the any kind of the contaminants, like in this case the it will be this, if there is a presence of the hydrophobic surface, make it easy to clean the car's body and basically looks better. In this case leads to the better finish and prevents any kind of the oxidation over the time. And of course it try to remove the avoid the chemical strain and the etch mark. So that is the purpose of ceramic coating, and the ceramic coating is basically try to create the hydrophobic surface over the object through this ceramic coating. There are so many techniques in the ceramic coating. There one is the vapor deposition, chemical and electrochemical deposition is there, thermal spraying is there, sol gel method also there, atomic layer deposition, and finally the solution immersion. These are the typical techniques to produce the ceramic coating over the surfaces. And of course there are a wide range of the types of the different ceramic coatings can be done, and different thickness coatings can also be done over the surface. Now other point of view is that ceramic coating is basically huge application we can find out in case of the architecture, in case of the marine, aerospace, and the biomedicine field. There we can find out the huge applications of the ceramic coatings. Apart from this ceramic coating, is that it's a cost of the ceramic coating is usually low. Cost of this material is low. Preparation process is very simple, that we have already explained, the slip casting process or tape casting process also. And but at the same time, although the advantages in terms of the low cost, but at the same time, it is having very good and corrosion and the wear resistant properties. Thermal stability is also very good for the ceramic, because ceramic as the melting point is very, very high for the ceramic material. And mechanical durability is also very good. And at the same time, there is a possibility to produce the biocompatibility ceramic also. So there is, you can see, there is a wide range of application of the ceramic coating we observe in practical. Now, apart from the ceramic coating, we also use the polymer coating, which we consider one of the non-conventional metal processing technique. So this polymer coating is also very important. In this case, it is having the very good shielding effect using the polymer coating, and it usually protect the metal surface. And of course, polymer coating, there is a very high flexibility of the polymer coating is possible. So traditional polymer coatings is basically we use the polyurethane coatings, epoxy coatings, acrylic coatings. All can be, you can see the applications of this type of the polymer materials or polymer coatings we observe. And they are widely used for the protection of the metallic. This polymer coating is usually used to protect the surface. So, but apart from this thing, polymer coating can be functional also. We can make the functional surface also. For example, it can be adhesives, photographic film. They can act also in the form of a polymer coating, but they are functional. So, and of course, at the same time, it is protective, anti-corrosions, and also decorative also. That we can see the different paint also, the polymer decorative paint can be used, which is we can consider as a polymer coating also. So you can see there are different work done that can be done by the polymer coatings process. Even polymer coating also used to modify the surfaces. For example, paper coatings, hydrophobic coatings. This way, the surface can be modified by the use of the polymer coating process. Apart from this thing, but if you observe the different types of the polymer coating, the mostly organic. But of course, sometimes we can use, or they can use the ceramic or the metal particle also along with the polymer coating. So just to increase the durability, increase the functionality, and aesthetic part of the surface can be utilized in presence of the ceramic or the metal powders along with the polymer coatings also. And In general, the coatings thicknesses can vary from the 1 micrometer to 100 micrometer thickness, depending upon the applications or depending upon the requirement. But there are several techniques to perform the polymer coating over the surface. That can be blade coating, spray coating, thermal spray coating, pulse laser deposition, plasma polymerization, flow coating, spin coating, sol gel deep coating, and the grafting. These are the different techniques, the way we can create the polymer coating over the surface. Now another important topics, then steel processing. Now I am shifting to the steel processing. This is the another important topic related to these subjects. So before that, we have some overview of the what we can consider this is steel and other component. So that is one is that first you have to look into where the steel stands. So we can classify for the steel. Steel, simply understand the plain carbon steel is basically iron plus carbon. Of course, the solubility of the carbon is very limited. So up to certain percentage of the carbon can be dissolved in the steel. So based on that carbon percentage, we can categorize the different types of the steel. But usually, along with the carbon, there might be small amount of the phosphorus, sulfur, Mn, silicon, all can be there along with this plain carbon steel. But usually we can distinguish the main alloying component is the iron and carbon. Alloying component is the carbon here. So in that case, low carbon, plain carbon steel, basically we try to understand that the very low percentage of the carbon up to this thing, which we can consider as a steel, and beyond that, say I can say that less than 2% of the carbon, which is categorized as a steel, and of course beyond 2% of the carbon, we can say that is the cast iron. So the carbon steel, there are several divisions between the carbon steel. One is the low carbon steel, is the carbon percentage is less than 0.3%. But in the carbon steel, the basic microstructure, which is usually ferrite and the pearlite, do low carbon steel. Similarly, medium carbon steel, the carbon percentage varies from 0.3 to 0.8%, and in this case, the microstructure or phase there presents in the form of bainite or martensitic structure. And high carbon steel is a greater than 0.8% of the carbon, and it actually there might be the carbon can be present in the form of martensitic phase. So there we can see that the different way the carbon percentages are different, but overall we can see the different phase can be the different in low carbon steel, medium carbon steel, and the high carbon steel. But overall we can say that strength actually increases with increase in the carbon content, because in this case the martensitic is more harder than ferrite. Ferrite is the softest element in this case, and martensitic is the hardest element in this case. So that's why when carbon percentage is increasing, in general the strength actually increases. But at the same time, when strength increases, we can say the ductility and toughness decreases with increasing the carbon content. Now, once is the carbon steel, plain carbon steel, there is another alloy steel. In this case, the alloy steel is that in this case the alloying elements added to the steel usually in the very small quantity, but usually less than 5% to improve certain properties, usually the strength or hardness of the material. But when alloying elements is added to a much quantity, say up to 20%, to produce the special property such as corrosion resistance, for example. So in that case, we can say this type of material is called the alloy steel. So in this case, the alloy steel is the carbon we cannot distinguish based on the carbon percentage. Rather, we can distinguish here what is the highest amount of the other alloying elements presence in the steel. So there are so many alloy components: silicon, copper, chromium, nickel, molybdenum, vanadium, tungsten. So each and every element having their role to bring some specific properties associated with the alloy steel. Now, for example, in this case, there are different alloy steels are there. One is the high strength low alloy steel, micro alloy steel, merging steel, stainless steel, tool steel, silicon steel. These are the different names of the alloy steel. But in this case, the alloying elements varies the different way. One is the high strength low alloy steel. We can see this particular steel is applicable in case of the structural application, bridges, building. There you can find out the high strength application of the high strength low alloy steel. Next is the micro alloy steel. Micro alloy steel, it is basically acts as a substrate in this case. So margin steel is having the super high strength is there, as well as the combination of the toughness. Usually strength increases, toughness usually decreases, but in this case, the combination of the very high strength as well as the toughness is possible in case of the margin steel. Similarly, stainless steel is basically known as the corrosion resistance property. So in this case, the chromium, we can get a very high percentage of the chromium that actually bring the corrosion resistance properties in the stainless steel. Similarly, tool wear contain carbon, contain manganese, just to improve the hardness and toughness. Low level of the sulfur and the phosphorus just as impurities is there, and that actually influence the properties like machinability and brittleness properties can be imparted using in presence of the sulfur and phosphorus in steel. But if too much of sulfur can be reduced just by reducing through reaction occurring between the slag and the metal is in the steel making process. So basically formation of the slag, the sulfur can be removed in the steel making process. But if you steel, there are so many different types of the steels has been developed as per the AISI. So AISI, there are steels, different types of the steels are produced, but there are different nomenclature depending upon the as per AISI specification. So AISI, there are 4-digit number, but first 2 digits indicates the what class of the steel and the major alloying elements, and second last 2 digits indicate the carbon percentage, carbon content. So here you can see, for example, the AISI 1018. If you take the first example, the steel type. So here 10 indicates it's a plain carbon steel, but 18 indicates the percentage of the carbon. So 0.18 divided by 100. So 0.18 percentage of carbon is there. That is the indication from this index, from this nomenclature, we can understand this thing. Similarly, alloy steel 5160. 5160 is 51 is a very specific type of the alloy, and 60 indicates the 60 divided by 100. That means 0.% of the carbon. Other components also, but that depends on the what type of the steels are there. So that indicates that, for example, alloy steel having apart from 0.60% of the carbon, it is having the Mn, sulfur, phosphorus, and other 0.08 chromium. So type of the steel is basically the right hand side is basically major alloying elements can be identified just looking at the first 2 digits. We can take an example for the 41 series that actually indicates the chromium molybdenum steel. Similarly, 51 series is the chromium steel. 44 series molybdenum steel. So basically first 2 digits we can identify what are the major alloying elements, and second last 2 digits it basically indicates what is the carbon percentage. So this way, AISI specific, we can simply understand the what are the type of the steel. Now, if we try to look into that, what way the steel is actually produced, the introduction of the steel making process. So through a flow chart, we can explain what is the overall understanding of the steel making process. So first, the iron is basically collected, iron ore plus limestone, and it basically sinter plant. This limestone and iron are mixed up in this case, and the other plant in this case the added is the coal is also added, and the coal basically modified in the coke ovens. Then the sinter from the sinter plant and the coke ovens from their coke are added in the blast furnace. So in that cases, the blast furnace, this melting is done along with this iron ore. So deoxidation is here is done. In this case, basically we try to follow. In this case, we produce the iron. So iron is basically produced from the iron ore. So all other unwanted elements from the iron ore is basically eliminated in this case and try to produce this almost pure iron in the blast furnace. Now, once it is done, then we can add the scrap metal also, because scrap metal can be added here along with the basic oxygen is added in the steel making. And once the basic oxygen is added in the steel making, the steel making, so that can be done in the basic oxygen furnace. So here the amount of oxygen is basically controlled here in this case. And okay, so basic oxygen is there, steel making, and we make the basic oxygen furnace. That is the steel making. And apart from this thing, from the scrap metal, we perform the scrap metal electric arc steel making there, and basically converted to the electric arc furnace. present there. So therefore, the component from the basic oxygen furnace and component from the electric arc furnace can be collected together and put in the ladle. And of course, in this case, it is refined. The composition is this control. All the composition is controlled. And then after that, we perform the continuous casting operation. So from the ladle, liquid steel is poured into the continuous casting system. And from the continuous casting, you can produce the semi-finished products. For example, in the form of a blooms, billets, slabs can be produced from the as a direct outcome from the continuous casting system. So once we get the semi-finished product, from there we perform the rolling operation, and usually the hot rolling mill, their operation, then we can produce the different this component, which is we can output the different steel construction product. Final products can be reached after the rolling operation. So different channel, cylindrical, the cylindrical object, all can be produced through the rolling operation. So these are the basic steps associated with the steel making process. Now, another important in the steel making is the single crystal production. So single crystal production, we know the single crystal production is one, and it is having lots of applications. And usually in the aerospace, power generation, automobile engineering, we can find out even turbine blade, engine component. Okay, all where you can find out the all application of the single crystal component. But single crystal materials are not what we can put in the steel making process, but here the process is something different, because the solidification process is usually controlled in the single crystal production system, such that uniform and continuous crystal structure is maintained during this process throughout the entire material. So here the heat extraction from the metal is basically controlled and it is directed in one direction, heat controlled extraction of the heat, such that only single crystal, single grain will produce, and just to avoid formation of the multiple grains or polycrystalline structure. So here single crystalline are composed of the very single uninterrupted crystal lattice is produced, and because presence of the grain boundary is basically actually decreasing the yield strength, and more importantly, and decreases the creep strength also. So, and creep strength is very important, the high temperature application. So by producing the single crystal structure, we can improve the creep properties of the material, and at the same time we'll try to produce in a single crystal structure just to produce any kind of the crystal defects, try to avoiding the formation of the different types of the crystal defects in terms of the dislocation. So here high performance industry can find out all these applications of single crystal structure, and one important is the turbine blade, engine components. We can find out the application of the single crystal structure. So of course, there are several techniques to produce the single crystal, and there is a development of the techniques, gradually advancement of the techniques to produce the single crystal structure. And nowadays it is more controlled way single crystal production can be done. So one of the important single crystal production technique is that is the zone melting process. So zone melting process, we see zone melting process is very, the phenomena is very simple philosophy here. In this case, this is the very controlled position, the very selective zone. This heat is basically focused on the selective zone and melt that particular zone. And once melting, and that melting front, or maybe I can say that melting front is gradually moved. Along with the synchronizing with the solidification speed, this molten pool or molten selective zone is basically moved one particular direction. So in this process, so when molten zone is created, the impurities is basically try to collect this, just try to gather of the molten zone, and then the continuous movement of the molten zone, and gradually other side there is a solidification also occurs. So during the solidification, you try to produce the single crystal structure, but the impurities actually filter and moves through the movement of the molten zone. So that's why it is called the zone melting process. So once this molten zone can be shifted gradually to a one side, then all the impurities is basically collected from that part, and it is discarded from the this complete component. So this way the zone melting is basically one of the simple and effective method for production of the single crystal structure. Now, we'll try to look into the steel solidification also. So the steel solidification, when you look into the basic structure of the steel, if you see the iron carbon equilibrium diagram, we can get some understanding of the different phases present here. So, but the solidification, that different temperature, these different composition, it will produce the different phases. For example, in this case, we can find out these four single phase structure. The liquid phase is there, delta ferrite, alpha ferrite, and the gamma austenite phase. These all are the single phase, and existence of the single phase at the different temperature and different composition also. So you can say the alpha ferrite is basically stable, the solid solution of the carbon in BCC iron. So basically the alpha ferrite is crystal structure is the BCC iron, but carbon is present, the carbon, the solution of the carbon within in this for alpha ferrite is the limited to only 0.22 weight percentage of the carbon, and that actually happens at the eutectic composition. So maximum solubility of the carbon in alpha ferrite is 0.022% of the carbon, and that actually happens at eutectoid temperature, that is at 727 degree centigrade. Similarly, gamma austenite exists is basically the wide range of the this thing. We can see the austenite is basically exist over a range of the carbon percentage, but some maximum solubility of the carbon is basically 2.14% of the carbon can dissolve in a the austenitic phase, and it creates a solid solution of the carbon in FCC iron. So here the crystal structure is different. So basically BCC iron is the room temperature, low temperature phase, and alpha ferrite, and FCC iron is the high temperature phase, and that is all the austenitic structure. Now, in this case, it will produce the the maximum solubility is existence of the maximum solubility of carbon, but that is around 1147 degrees centigrade. Similarly, delta ferrite also. In this case, the delta ferrite is the solid solution of the carbon or BCC, and that is also high temperature phase. So here, solubility of the carbon is actually very low, but its existence of the delta ferrite is around 1394 degrees centigrade, but melt occurs here 1538 degree centigrade. So just looking into this phase diagram, we can extract information about the different phases, their existence, and what are the reaction easily occurs at the different point. For example, here you can say that eutectoid temperature. So eutectoid temperature, there must be some eutectoid reaction. There might be some eutectic reaction. That information can be obtained from this phase diagram. But of course, this phase diagram, we are talking about the phase diagram, but we are saying that iron carbon equilibrium phase diagram. So basically this phase, existence of this phase is under equilibrium condition. Of course, if there is a variation of the change of the cooling rate, in that cases, this we cannot exactly follow the equilibrium phase diagram. So here some example is that, for example, eutectoid steel we are talking about, but eutectoid steel is basically corresponds to the 0.778% of the carbon. So in this case, it creates the parallel structure. This parallel structure is basically a mixture of the ferrite plus cementite, and it's create very specific pattern of the parallel structure. So it basically creates the alternate layer of the ferrite and cementite, and that is the typical characteristics of the parallel structure. But parallel, we can say only this particular structure, but at exactly the carbon percentage of the 0.778% of the carbon. So basically this reaction occurs, one solid phase is basically decomposed into two different solid phases in this particular case. Similarly, we can say that in low carbon steel, we can find out the hypoeutectoid steel. That means whatever reaction is actually happening in this case, the carbon percentage is less than the eutectoid steel composition. That means less than 0.778% of the carbon. So any reaction below that, we can term as the hypoeutectoid steel, or any composition beyond that, below that 0.778%, that will create the hypoeutectoid steel. Similarly, first is the hypoeutectoid steel. We can see, but they can create the different composition in this case, but depending upon the it can create different structure. You see here also hypoeutectoid steel, it creates the ferrite plus parallel structure. 0. near about this thing, even hypoeutectoid steel can be ferrite plus pearlite structure, but it depends on the what type of the this thing phases from which phase to another phase is basically transforming. Based on that, different structurally it can be different depending upon the carbon percentage in case of the hyper-eutector cell. Now, similarly, if you look into the hyper-eutector cell where the carbon percentage is more than 0.778% of the carbon, in that cases we can create, it's a mixture of the ferrite plus pearlite usually in this case. But overall, it's a consist of the ferrite plus cementite structure in case of the diagram between the iron and iron steel. So that's all. Thank you very much for your kind attention. Now we have any query, we'll try to look into this. You have any query, you can raise the query, I'll try to answer them. So I think there is no questions raised, this thing. There is no questions raised here. Hello, yes. Okay, so I think I can close this session. Okay, yeah. Thank you.